go. Where is it? Here we go. So week 6. So we are in week 6. Oh my god, time fly. That's crazy. So we are like in the half of 3 months. 6 more weeks and we be done with this LeetCodes. So this PLD today we have the 3 first one, implement queue using stack. We already did something similar like this. We did like implement stack using queue. Then we have first bad version. Then we're gonna do Ransom Note. Okay, let's start with the first one. Let's see how we can solve this mystery. So let's see the problem. Implement queue using stack. Implement a first in first out fee for queue using only 2 stack. The implemented queue should support all the functions of a normal queue: push, pick, pop, and empty. Implement the myQueue class. Void push element X to the back of the queue. Int pop, remove the element from the front of the queue and return it. Int pick, return the element at the front of the queue. Boolean empty, return true if the queue is empty, false otherwise. So not, you must use only standard operation of stack, which mean only push to top, pick pop from top, size and is empty operation are valid. Depending on your language, the stack might not be supported natively. You may simulate a stack using list or DQ double-ended queue as long as you use only a stack standard operation. So I think some of you may remember we did something similar to this. We did like stack using queue.
Like this.
Yeah. Now we're gonna do like the reverse. We're gonna do queue using stack. We can see some example. So we call myQueue right here, create a new instance of myQueue. Then we push with argument 1, and this have return null. This also return null. Then we push 2, return null. When we did pick, it show us 1. When we did pop, it show us 1. Empty, false. There's still something there. There's still 2. So we are implementing queue using stack. So because we push 1, the first one we did push, so when we're gonna pick or pop, it should show us 1. I guess that's the explanation. X can be from 1 to 9. At most, 100 call will be made to push, pop, pick. Okay, all the call to pop and pick are valid. Follow up: can you implement the queue such this operation is amortized or 1 time closely? In other words, performing in text. Okay. Oh no, I didn't see. Sorry, don't kill me. Okay, so follow up: can you implement the queue such that each operation in what does this mean?
Amortized, it means the average compute time is going to be that.
Oh, 1.
I think, okay. But you can just Google it just in case.
Okay, I can't read all of this. Let's check. Give me short.
You've got best case, you've got worst case, and then you got average case. Amortized is the average case.
Average case. Okay, I think ChatGPT also didn't understand. Okay, let's go with average case. In other words, performing an operation will take overall on time, even if one of those operations might take longer. Okay, let's just explain queue and stack just quickly so everyone can follow. So if we said queue, we're probably gonna imagine it like this. And if we say you are a person, you're gonna enter the queue. And so you're gonna enter, someone come after you. Someone come after you, so he gonna enter too. Someone come after him, he gonna enter too. And when it is time to serve, like maybe you are gonna buy something, if it is time to serve, of course we're not gonna start from this one, we're gonna start from the person that's come first. So this is the queue. So imagine serving is like pop, or like when we peak, and the difference between pop and peak is like when you peak you just check who is there, right? But when you pop you actually serve them the request and they go out from the queue. So when you pop elements you remove it from the queue. When you peak is just like you check who is the first line. Now the same thing for the stack, but stack we're probably gonna imagine something like this, and probably gonna think that we are washing dishes, right? So we wash the first dish, or like we stack the first dish that we want, like we put first dish, then we put second dish, and probably after a bunch of dishes we wanna like clean them. And of course we're not gonna go and clean this one, right? Because we can't, because stack is, you can imagine stack is closed from here. So we're gonna start from the last one. So that is our pop here. It's gonna also always take the last one and pick two. And yeah, so this is queue, this is stack. Now what they are trying to do, or like tell us, is implement queue using stack. What that mean? We did before implement stack using queue, but in this case we're gonna have stack like this, but I want it to behave like this. So if I put a dish and then another dish, another dish, another dish, normally because this is a stack, if I wanna pop or clean a dish, I will check this one, last one, right? This is behavior of queue, stack. But what they're saying, no, like if I did pop, I should clean this one. I should start from this one, the first one that's entered the stack. So our pop gonna be popping this right here, the first one. We're gonna pop this one. If we did pop, it's gonna need to pop this one, or if we did pick, it should give us this first element. Now did it give us something is to implement queue should where is it? Implement using only two stack. So we can get the help of the, let's say, another stack. I can do this like this. We can like have the help of another empty stack to implement this. So we have one stack, two stack, stack 1 and 2, and we should do this. Okay, who didn't understand what they want us to do, or who is have any question related to queue, stack, or any question in general before like we start brainstorming how we can do this?
I'm sorry, I came a little bit very late. Please, can you just tell me the name of the
Yes. Okay, so I will paste it here in the chat.
Okay.
Someone got dizzy. Oh no. Okay. So I will repeat quickly. So I think you were with us when we did the stack using queue, right? We implement stack using queue. This time we're gonna do the reverse, is we're gonna implement queue using stack. So basically we know how this stack reacts, right? And how queue reacts. This is the queue. If I'm gonna pop something from queue, I always pop the first one that's entered, right? But if in the stack I'm gonna pop something from stack, I always pop the last one that's entered, right? So when I'm gonna say implement queue using stack, what you're saying is like you're gonna keep the same stack, like you're gonna have a list or wherever, but when I'm gonna do pop, I should get the this one, the first element that's entered, right? For example, if I have array and I put 0, 1, 2, 3, right? And I did to this array pop, which element's gonna give me? It's gonna give me the list, right? The last one that's entered. But because we are implementing the queue, somehow it should give me 0. When I do pop to this array, it should give me 0. If I do pop again, it's gonna give me 1. And each pop, it removed elements from array. And we can get the help of using another empty array. So array 1 is 1 is 2, and we should do this implementation of queue. Okay, who have a question about like understanding of problem? Make sure we all understand what they are asking us to do, then we can jump to brainstorm solution, how we can do it.
Okay, I just want to bring up something. Like, they're kind of saying that we could use, let's say, 2 stacks. Well, I was kind of like in my mind, like, why do we need 2 stacks? Like, can we just have a data structure that maybe we are maybe popping out stuff that kind of open-ended? We can access it from the left, and access components on the right. We kind of like the rationale between.
But you see, that would be cheating, my dear Ernest.
Yeah, like because if you use DQ, we actually have pop and pop left, so we can jump to doing it easily. But it will be fun if we can do it like do it in the normal way, just by using a normal stack behavior.
Yeah, the whole challenge is that you have to use a stack to implement a queue.
We can create 2 stack. The first stack
I think
is the principal, and the second stack is the reverse. So the first.
Okay, before we jump to the solution or brainstorm, is like everyone understanding what we're trying to do? Please, if you're not, I can repeat, or I can clear if you have some question or someone here. Okay, I guess not. You can type in chat. Okay, so let's see. Let's go to brainstorm. How are we gonna do this? So let's say we have S1. This is our stack, and we have S2, right? And okay, and we have this empty stack right here. Let's call them S1, S2. And let's just say we have, for example, this value like 0. let's say 3, 2, 1, 0. What did you say? Q is in stack. So this is our Q, and somehow we need to use these same numbers, and when we pop we get this one. Next pop we get this one. And using it in this stack. We can say let's design our stack like this, so we don't. It will be more easy probably to imagine. Okay, so this is our 2 stack. S1, S2. Okay, let's brainstorm. Pop 0. I think that's also cheating. Or not? Maybe not. Maybe not. Okay, let's make something clear. Push. What about push? Do we leave the push the same? Because if we notice right here, the push is the same behavior, right? If I push something,
Exactly, yes.
it's gonna be
Insertion is
same.
on the same side.
Yeah.
That's correct.
So we can just leave push append, for example, in Python. I think append. So we're gonna just append stuff. But when we're gonna pop, it's gonna be a problem. So the problem is in the pop. So let's say they give us 0. The person 0 come first. I do append. Okay, nice. 1. Okay, nice. 2. Nice. 3. I'm gonna do pop. It's gonna give me this. Okay, we have problem. It should give me this. So how we can do this using another helper? Reverse the stack to pop and reverse it again to append.
Sorry, please, can I say something?
Yes, please go ahead.
Okay, I think we can use the logic we used when we were working on implementing a queue using 2 stacks. I think we can, implementing a stack using 2 queues, right? I think we can do the same here. For example, if we want to pop from our queue now, right? We'll copy everything to the other queue and then pop from front, like pop from the last element that just entered. I think that would make sense. Like copying it to the next queue and popping it.
Okay. So you're saying we're gonna pop when we're gonna pop, we're gonna do 3, 2, 1, because we are like moving this element, right? Move this here, move
Exactly.
this here, and then
Yeah.
we're gonna pop from the second stack. Okay, this will work. If we pop from the second stack, we're gonna have 0, which is exactly what we want. What's
Nice
about
idea.
this? What's about this
Nice
idea?
idea,
I think reverse the stack to pop and reverse it again to append. So we're gonna
Nice one.
reverse this one. Yeah, this is smart too. Yeah, just reverse it. It's gonna give. So in this case, we don't need to use 2 stack. But
What
we
about
do-
if is there a way to get it by the index? Is it possible?
this one?
Like when you want to pop, you can pop it and also using it as an index. Like you can pass the index into the pop. Is that possible? I'm just asking. I don't know.
I think it's possible, but it's kinda cheating. Just like to respect the what the task is asking us. It will be cheating, right?
that's fine.
Because
that's fine,
because
that's fine.
we can use, for example, DQ, and we have pop and we have pop lifts. So basically, I'm gonna just pop lifts and it will work.
Exactly. That's nice.
Okay, do we use this idea of moving between 2 stack? I think this idea is cool.
Yeah, that's cool. Reverse it, then remove it. Yeah, it's okay.
But there is a problem, a small not problem, but like this one here. Follow up, can you implement the queue such that each operation in is amortized? Amortized? Okay, give me a second, let me learn how to pronounce this.
Amortized.
Amortized. Okay. That each operation is amortized O1 time complexity. In other words, performing an operation will take over all ON time, even if one of those operations might take longer. So if we did it this way, we're gonna have ON, right? But we need somehow to reduce this way, or like reduce, because now each time I'm gonna push something, I will push it normally, and each time I'm gonna pop, I will move all of this to here, and then I will pop the left one. So that is ON. Like the pop
And I
is
think
gonna
even
be ON, right?
I think even after popping, you have to readjust back the previous stack, or you can't just leave it like that. Just kind of try to maintain the way it was before you adjusted it, something like that.
Wait, can you repeat what you said?
I think like because you are using another stack, right? You are using one to adjust the other. So maybe after doing the change, you have to maybe readjust back the previous stack. So I think you may have end up like with two ends. Like, although it will still kind of be off.
Yeah, it's a two-way thing. You're right. He has to go reverse, then go back again to the original stack to move the items again back there. So I think it's a two-way thing.
It is 2 and it is ON, right?
Yeah, so it's really very inefficient, and we are not following the instruction properly.
You know, if you're reverse, I don't know. I don't think it's ON. I don't know, but I don't think it's because it's twice. It's twice you're doing it.
Because when you're gonna reverse, the reverse is gonna depend. No. We're not talking about the reverse. We're talking about the solution of transferring each one to the second stack. The reverse side, no.
But then you have to do the operations twice, right? Because you after doing that, you're not just going to leave the the second stack. You won't just leave things in memory like that. You have to adjust things back to the previous, because after removing that O, if you are creating if you create another stack, you have to kind of go back and readjust that first one to accommodate the fact that it doesn't have the 0. You put out 0. So I don't know if you guys are getting me.
Okay, wait. Let me try to imagine what you're saying in the board. Okay, so the idea that I get is like, so we push 3, 2, 0, 1, 2, 3, right? And then I'm gonna pop, right? Now before I'm gonna pop, I'm gonna take this here, and then take this here. Now this operation is gonna take ON, right?
Yeah.
Exactly.
Take this, and then when I take everything from the stack, I'm gonna get this last element with pop, right? Now this operation is ON.
Okay. But then if you kind of have to maintain.
So are you going to empty the first one, the first stack? Would that be empty, or you have to still copy back to it? So what's going to happen to the first stack?
Yeah, that's the question.
I guess if I add, so we can do something is like, let's say I'm gonna pop again because I'm popping from the stack too. So I did pop this, right? Now when I'm gonna pop again, I'm gonna pop from here. Pop, pop, pop. But what if I add some element? Let's say 4, right? We have 4. Let's say pop 1, 0, and 1, and someone did push 4 to the stack 1.
Yeah, 1 is
Uh,
okay.
It doesn't
That is
it doesn't affect
that's
the
what
pop,
I'm
right?
saying.
It doesn't affect the pop because I'm still
Okay.
popping from stack 2.
Adding to the other one. Okay.
Because if I pop, I don't care about 4 that's here. I can just do pop and pop 3. And now that the stack is empty, when I'm gonna pop, I'm gonna do the same thing. I'm gonna transfer everything in stack 1 to here, and then pop. Like we did in the beginning, right? Because this one, we were here at the beginning.
So let's say, okay, if you had, let's say you had some values in the stack 2. Let's say you had not popped everything.
Like this.
Yes, and then you had to add something from.
Let's start from beginning. Let's say stack 2 is empty. Now I'm gonna pop. I'm gonna check. Okay, is the stack empty? Yeah, it's empty. So automatically I'm gonna transfer everything from stack 1 to here. Now that I transfer them, I can pop the last element. Right? If someone push something here, it doesn't affect my. Yeah, like you can pop 4, 5, 6. I'm still. If I'm gonna pop from here. Pop in, right? Pop in. I'm gonna pop again. The stack is empty, and because it's empty, I'm gonna do the same thing.
That's when you add. Oh, I see.
Because it's empty. So this way we reduce this transformation, or like we reduce the what is it called?
Exactly. You reduce the
It doesn't become ON. It's kinda reduced, right? Because we move elements from stack 1 to stack 2 just from time to time, not all the time.
It means you kind of have to always check if stack 2 is empty before
to pop.
you move element.
Yeah. You can do like a while loop. No need to put numbers back to the stack 1. We can rename. Yeah, this also can work. Like flipping between them, but might be a bit complicated. Maybe not. I'm not sure.
So that means that your peak will almost behave like the pop as well. Your peak, the peak function.
Yeah,
will behave like the pop as well.
Yeah, the
just
peak,
to check the second stack.
Yeah, the peak and the pop always should behave the same. The only difference is peak gonna just check without removing it, but when you call pop, it's actually remove it.
Yeah, I'm just talking about the implementation, because if it's for peak as well, you also have to check. If it's empty, then it has to do the whole reverse and stuff, like just like the way the pop is behaving as well.
We can do it actually in peak, right? And when we're gonna try to pop, we're gonna just call peak, and then pop the last element of stack 2, because peak will
peak will return exactly.
We'll do this transformation.
I think as long as you're not like traversing through elements, it's O of 1, right? Operations are not counted. It's like it's a looping that is actually counted. So more of like if you're copying from one place to another, operations within maybe within the programs are not counted in terms of complexity. I don't know if you guys. And so with this, I think we can still achieve O of 1 with this method.
I believe so.
As long as this,
maybe.
Yeah.
If we have fixed sizes, we are just checking whether one is empty or not. If one is empty, if S2 is empty, they want to copy everything from up there and put there. So we kind of, is it possible to copy without traversing through? I think in C that'll be easy because you can just copy the memory locations.
Yeah, but the key is in the follow-up of the question. The amortized, however you pronounce it, it states that on average, right, you won't have to perform the reshuffling of the lists or the stacks. So essentially, you'll be dealing with that O of 1. But in the case, as Munsif showed, when you do deplete the contents of the second stack, you will then have to do something that's going to take O of n time. But that won't happen on average all the time. It'll only happen just a few times. If, like, worst case scenario, it's push pop, you know what I mean? And you have to do it every second, or something crazy like that. But on average, you won't have to do this reshuffling thing. So, you know what I mean? It kind of gets lost. It's not going to be totally inefficient, but it isn't great.
The key is on average.
Yeah, on average, it'll be fine, but
Yeah.
One or two bad scenarios, but as long as okay, that makes sense.
I think this solution is better. So I think Ricky also suggests that we do append that can append by adding to the start and moving the previous item to the end, so that the poppable item will be first. So like if I push 0, if I have 0 in stack and I want to push 1, I will move 0 to the other stack, then push 1 and then put 0 here. If I want to push 2, then I will put both of them here and then put 2 and then put them back.
That's a lot of operation going on, really.
Yeah, so this way I keep 0 first. This will work, but we want something close to 01. I think this is the only way to do it. Maybe there's another way, but this one is gonna get us close. So maybe let's work on the pseudocode for this one. Let's do it one more time just to see how it's gonna work. So we have stack 1, but someone have the helicopter on. Aridwan Olai, if you can mute your mic until okay, till you wanna talk, feel free to open mic and talk. So we wanna do something like 0. So what we said, we push 0, right? It's come here. We push 1, it's come here. We push 2, it's come here. Then we push 3. Now time to pop. Now when we're gonna pop also from stack 2. We're gonna pop, or there is nothing, we do a check. If there is nothing, automatically we bring everything from here, from stack 1. So 3 gonna be first one, 2, and then 1, then 0. When we move them all, then we pop the last one, right? Now we pop this 0, and if they pop again, it's gonna pop 1, it's gonna pop 2, it's gonna pop 3. If it's gonna pop, it's empty, it's gonna check if stack 1 is empty, then there is nothing to pop. But let's say someone did push 4 and 5 here, right? When we're gonna keep popping and we're gonna pop again, what we're gonna do, we're gonna check if this is empty, then we're gonna just check the stack 1 and then move this right here. So it's gonna be 6, it's gonna be 5, it's gonna be 4. So when we're gonna pop, it's gonna give us the last element, which is 4. So this way we don't transfer between stack 1 and stack 2 that many times, like each pop. We just transfer the band.
Are the stacks supposed to have some size or something?
Can you repeat?
The sizes of the stacks, are they kind of fixed, or the size component?
Let's see. So x can be from 1 to 9. What is x? I guess X is the number that we're pushing.
Yeah, the elements.
I think it didn't say any. So this say 100 call. Yes, that will be a lot. Okay, let's see what is our function. Okay, this is the functions we have. We just put it close to us to stay focused. Okay. Let's move to a new place. Maybe here. How we can implement this? So we have these two stuck, right? Okay, maybe remove this. Okay, we have these two stuck. Now we have what? Pop. Let's start with init. What we're gonna do in init? Stuck 1, stuck 2, right?
Yeah.
Call it S1.
Okay.
Self. Okay, let me zoom. Self that S1. Self that S2. So push, we said we're gonna push in S1, right?
Yeah.
So if we push, we always push here. S1, nothing changed. So it's gonna be something simple. Self that's S1. That's append X. And that's all. Now empty. Let's check empty later. Pop, we can use pick to pop, so we can code this functionality of getting the last element in pick, then we can use it to also do pop, because if I can pick the last element, then I will just pop S1, S2 -1, right? I can just pop the -1 element in the S2.
Yeah.
So how do we start? We said that we push element here, right? Let's do it. Let's see how we can do it. We have like 1, 2, 3, and we say when we're gonna do pop,
You have to check if it's empty first
we're gonna check.
before you even start.
Yeah.
We're gonna check if stack 2 is empty.
Yeah.
Yeah.
So we're gonna do if. Wait, yeah, let's go with it. If stack 2. If not stack 2.
If not, yeah.
If not.
If not,
If not
self.
stack 2.
Okay.
Yeah, I will write it later there.
I think.
So if the stack is not, if not stack, it means if stack is empty.
Yeah.
So if stack is empty, I will have to bring back this one to here.
Yeah.
So
Why not use the len? Would that work? Sorry.
yeah,
And why not use the len?
yeah, we can do len stack
Length of stack is
S2
zero, yes.
equals 0, right?
Yeah, that's better.
Okay.
Yeah.
Because this is still the same as
Yeah,
the
it's
empty
readable
bracelet.
like this. Okay, so if length of S2 is 0, then I need to bring this one here. So how I can bring this 3 here? First of all, I know this. To select this, I use pop. So S1 pop. This gonna bring me this element. Now I want to append it to this one. So I can do S2 append, and what I'm gonna append, the thing that I pop.
Yeah.
But I wanna keep
I
doing
thought you
it.
said I thought you said that you are going to reverse it to the next stack. That was what you said, right? Or did it change?
No, we're doing
Like
the
you're going to reverse everything.
Hello.
Okay.
we're doing the solution where you move element to stack 2. Like we are using 2 stack, not 1 stack. The reverse gonna use 1 stack.
I know. Like what you said before was you're going to move everything in S1 to X2 in a reverse manner, right?
Oh yeah, that's what you're doing. Like okay, like notice
Okay.
the animation
Okay,
here.
go ahead.
Like notice the animation here. If I move this pop, isn't it gonna be reverse? Then I'm gonna pop this. Did you notice? It's reverse, right?
Okay, yeah. Go ahead. Yeah, go ahead.
Yeah.
Sure.
So because pop is gonna pop the last element, and append is gonna append it to the last. So it's kinda
Yeah,
reverse.
I get. Thank you. Yeah.
Okay, Grace or someone have mic open. You have background noise. Please mute.
Sorry, I think that's
Grace D. Please mute your mic. I think he's talking to someone else. Okay. Okay. So what? So this gonna move this here, but we wanted also to keep moving this and this. So while loop.
Yes, we need.
So a while loop that's gonna keep going until the stack 1 is empty. So while the stack have something, keep doing this. This part is clear, right?
Yeah.
Okay, now what we did so far is we move elements all from stack 1 to stack 2 if the stack 2 is empty, but we still need to pop the left one or the right one. So I guess we can do after the while we can do pop. Is to
Just return pop.
yeah, return it. Return pop or return. Wait, this is peak. We're doing peak, so we can't pop. So we're gonna do -1. Because this is the code of peak.
I think pop is working.
If I did pop, it's gonna remove it from the stack. And peak, it doesn't remove, right?
So we need to remove.
yeah.
Wait. Are you talking about pop or
because
peak?
You're correct. Peak does not remove.
That's peak or pop? I don't know.
Okay, so like in peak, peak you don't remove, you only peak.
Okay.
Yeah.
Yes.
So like in peak you're gonna just check who is here, but when you're gonna pop, it's actually remove them.
Okay.
So because we are coding peak right now, we can't do pop
Sorry.
because we're gonna lose that element.
Okay.
Okay, sorry. I don't think we should return in this our if statement. I think it should be after the if statement.
Yeah.
After if statement.
But not inside the if statement. You know, this if is only when our second stack is empty.
Oh yeah, that's smart because we only enter here to transfer the stuff, to transfer the elements from stack. So when we finish, then we're gonna return, because if we didn't do that, we're gonna we're gonna do this, which is not gonna.
So are there cases where somebody can do a pick on an empty stack? Just asking, I don't know.
Let's see. Empty stack.
Like somebody just want to, okay, you go and do a pick and it's empty, you know? You understand what I'm saying? Where nothing is inside. The person went to do a pick to check. So what's supposed to happen?
I'm not sure. Let's see if they give us.
Sorry, hello.
Yeah, hello. Hello.
Yeah, please, I just want to make a clarification.
Yes, please go ahead.
Regard this question. Based on the what's it called? Sorry, I'm coming over. I read some explanation given. We check the explanation side. It said my queue dot push 1, my queue dot push 2, which is 1, 2. Leftmost is front of the queue. My queue pick return 1.
Yes.
Return 1 in this aspect, that doesn't mean that it removed 1 from the first stack.
Yes.
So my queue dot pop return 1, and the first stack still remain 2.
Can you repeat last part, please?
So my question now is that with the illustration in which you gives here, it seems you are using pick to removed.
No, pick doesn't remove. This one?
Yes.
But this one doesn't remove it, just return it.
Okay, just return it. Okay.
Yeah, so what's here, what's -1 mean? It means you're gonna check the last element of array.
Okay, but I'm of thoughts. Okay, no problem.
Yeah.
But in case if you want to loop this second stack, won't it start from the first place? Assuming you want to loop through, maybe at the outcome they give us a kind of function of printf. You know, if you want to printf now, based on this your stack 2, it will start from 3, 2, 1. Why can't we just do it in a sense that our 1 will be at the leftmost side and 3 will be at the rightmost side? I don't know, maybe I'm making sense.
No, you make sense. So what you're saying is like, why not at the beginning we can push 1, 2, 3, right?
Yes.
Yeah,
because if we're given a loop, another printf, and we're told to, okay, print s2, or or better still, they have already they have their own functions, printf functions already prepared for us. In a situation like that, that means in that situation now we'll be printing 1, 2, 3.
Yeah, so like the way you said it, it's possible we can do that, but it's the task itself is like just a tricky task. Is like, hey, you're gonna implement the queue using stack. So like this this long way to do it is kinda intentional. It's not like, oh, this is the only way or this is the best way. Of course it's not. But the task itself is like implement the queue using stack. So yes, of course I can just order them when I push as I want, but it's like, hey, you're gonna push them this way, but I want you, when you pop this one, right? So we have to go through this trouble to do that, you know, just to satisfy the task. But yeah, your point is good. Okay, so we did the peak code, right? This one. So what this code gonna do is, if, okay, this should be inside, if the stack 2 is empty, then we need to while s1, so we're gonna transfer the elements from s1 and append them to s2, right? Now let's say we did append them, then if I did pick, I should return this. I return it without delete, right? Which is what we have here. Okay, please, if someone have question about this part of pick, if you didn't understand how it works or something confusing, please go ahead, ask your question in chat or in the mic. Okay, if it's all clear.
So you didn't.
Yes.
Sorry, Musif.
Yes, go ahead, please.
That means that there are no cases where somebody will go and pick into an empty stack, right? There are no cases like that.
Oh yeah, we were thinking about that. Okay, so let's see if they mention something about it. Okay, they didn't mention anything, but they say.
All right.
I don't know actually what could happen. Is
They
it
mentioned
gonna...
it. They said all the calls to pop and pick are valid. So they cannot call a pop or pick on something that's not valid.
Okay, nice.
Oh, all call valid. But that doesn't mean it's not empty, right? Or that is something it mean.
No,
It
it's
means
okay. We
that-
can ignore it. We
Yeah.
can ignore it. Maybe when we test it, then we'll see.
Yeah,
You don't
but
need
it's a
to-
good
yeah,
question.
Just continue.
I think
Let's
what
see. Yes, please go ahead.
I think what we can do is like when we have an empty stack, that is our S2, right?
Yeah.
Like after we get everything from S1 to S2 and it's still empty and it's a peak, then we should return an empty stack instead of returning S-1.
Yeah, this is
Then
gonna
if you
give
get-
error, I think.
Yeah, if it
Yeah.
is empty.
Yeah,
We'll
we can
check
try it. We can add a test case and try it. But let's say
Yeah.
this edge case is not in the way, and let's just go with the. So this is pick. Now we wanna do pop, right? So the idea was like, just add peak inside pop and then check, then pop the last element. So like in the pop itself, we're gonna just call self peak
That's very smart.
and then self pop. No, not pop. What's it called? S2? Yeah. Because when we're gonna pick, we kinda guarantee that the element's gonna be arranged in a way we have access to the last element. So then we can just do S2 pop. Then I think that's all.
Okay, you have to reference your S2.
Okay. Return it.
Variables inside the class must always have a self. Self.s2 inside the len, and then while self.s1
Oh, yeah.
also.
I guess here we're gonna return it, right? When we're gonna pop it, we're gonna return it. This is gonna be self.
Yeah.
It's gonna be self. This is gonna be self.
Inside pick.
No, I thought the pick does it already. Pick will do it, right?
But it's not gonna pop it. It's gonna just show us that element. It's okay. Let's think about it.
Yeah.
It's gonna like just show this
Because
element.
there's a return in the pick. You get.
Yeah, but
You
it's gonna
understand?
show it. Like
Okay, just show.
yeah, but we don't wanna do anything with that value. It's like it's gonna tell us, hey, the last element is 1. But I kinda don't care what is the last element.
Yeah, I get.
But I can do like this, return, right? Return. It's gonna give us the last element, but the element itself is still
Has not been popped.
in the stack.
Exactly.
So I kinda forced to pop it. So I can remove it. Empty. Okay, who didn't understand this one? The mix of pick and pop. Who is like confused a bit? I guess no one, or someone is confused but is shy to ask. Just write something in chat. Don't worry. Don't be shy. We're learning together here. So, I guess it's clear. So, empty. What empty is supposed to do? How we can do empty?
I think you just check if the both stacks are empty. That return false if it's empty. If it's not, then return true if it's empty. Actually.
Oh, okay. That's a good idea. So return
So we
the
need to
length.
check both of two.
What they do? If length of S1 is less.
If length of S1 is equal to 0.
It is the same as 0, and the length of S2 is the same as 0.
Wait.
Yeah, because you have to check the two stack.
Yeah.
And length of S2 greater than. Wait.
I think it's or.
Or
I think it's or, right? It should
wait,
be or.
because
I think we didn't need to
Yeah,
use if.
why?
Just use return.
Now, do you know why it said or? Because if you put it like this, there are
yeah,
cases where someone,
or because
yeah,
one of
because,
them
yeah,
because one of them
exactly.
this way, yeah, this if we did and this may be empty, this may be full, and it will be false.
Correct.
Okay, let's run.
The S1 is not well referenced.
Oh, self, yeah. Okay, self. True. We have problem in this condition.
So we can use not.
Oh, maybe equal
Because
0.
Yeah, it used to be the same as 0 for all of them have to be.
Less than 0.
Can you repeat?
Can you just use an if condition? I don't know.
It's not possible for the length to be less than 0. 0 means it's empty. So if we are checking if it is empty, we should say less than 1.
Okay, this should return true if it's empty. Oh, yeah, so like equal?
Yes, true if it's empty, yes.
Okay, so wait, then we can do equal and end, right? Both of them are empty.
That's what I was
Exactly.
Okay, sorry. It's confusing. Oh, okay, finally. It worked.
Nice.
Congratulations. Let's submit, see what's going on there. Nice. Okay, 89.
I love this.
That's good. Okay, let me pause the code and let's jump to the second LeetCode. Please, if someone have question. This is the time before we jump to the other one. Okay, no one. Let's go to first bad version. Hey, Brayo, please mute your mic. There's a background noise. Thank you. Okay, so the first bad version is this one. Let's post the link. So you are product manager and currently leading a team to develop a new product. Unfortunately, the latest version of your product failed the quality check. Since each version is developed based on the previous version, all the versions after a bad version are also bad. Suppose you have n version, 1, 2, 3, 4, and you want to find out the first bad one, which cause all the following one to be bad. You are given an API boolean is bad version, which return whether version is bad. Implement a function to find the first bad version. You should minimize the number of calls to the API. Example, we have 5 version and we know that the bad version is 4, and the output of this function or algorithm, it's gonna say the first bad version is 4. Explanation, call is bad version 3. Okay, so this is the API they give us. It's like a function, you give it a number, it's gonna return 3, true or false. Let me check. The is bad version API is already defined for you. So the function we're gonna work on is first bad version. Yeah, it does smell like a binary search. So first bad version, we're gonna use is bad version. 3, 5 is true, 4 is true. Then 4 is the first bad version. Example 2, n is 1, output is 1. Okay, let's take this to the lab and let's slice it all. Okay, so how we can do this? The coach said binary search. So in this case they give us 5, right? 5. So 1. We start from 1 or 0. So we start from 1. So version 1, version 2, version 3, version 4, and version 5. And we know that this is 4, is the first bad version. But we don't know, like we can't know because we need to use the API. So if we use binary search, how we can do it? Like lower, higher pointer?
We get the midpoint and it will be 3. And just if 3 is bad, then the rest is bad. If it's not bad, then eliminate the first half, and we deal with 4 and 5.
Okay.
If 3 is bad, then we know it could be the first or the one before it. So we just keep checking the right half.
So I thought they're gonna give us a target, right? They will give you did they give us any target?
No, there's no target. We don't know what. We actually don't know which one is the bad version. We need to use a API that will return false or true. This API here is just a function, is bad version. So we're gonna give it true. So it's like, if we're gonna do it in brute force, I'm gonna just send 1 to this API, and they're gonna wait. True. Okay, so this is the bad version. So this is automatically gonna be the first bad version, right? Because there is nothing before it, right? But if it was false, I'm gonna check again 2. False. This is not the bad version. 3. It said true. Then I know this is the first bad version, right? But we wanna do it in a way optimized, like binary search. So dictionary or hash map with the version as a key and boolean as value.
So I was thinking, why don't we divide n into 2 using it as a, if we divide n into 2, we take the number and send that particular version. If it is bad, then we can know whether we are going to the right or we are going to the left.
Yeah, that is divide and conquer, right? It's the binary search. Like
yes.
Still binary search.
Yes, so like you put lower, higher, and you look for middle, like the coach said. So if the 3 is not bad, that means the bad is still in the other side, in the right side, right? If this is not bad, automatically we know this is not gonna be bad. Then we're gonna move lower to 4. Then we're gonna check the middle 4. If this is bad, if 4 is bad, I know that all the bad version is from there, but I don't need to check for 5, right? Because if 3 is not bad and 4 is bad, so this is automatically the first bad version. I don't need to care about 5 and 6 and 7, right? Because I'm looking at the first one. So as long as I find the first one, so yeah, that's it. I hope it's clear. Let's do one more example. Let's make it a bit larger. 6, 7, right? Let's say that the bad version is not 4. Let's say bad version is 5. 5 is the bad version, and we have a high. Now this gonna be the middle is 4. We're gonna check. We're gonna send 4 to the API. API gonna return false. Okay, so automatically understand that from 4 to the left, all these are safe. They are not bad. So I'm sure the bad version is somewhere here. So because that's set false, I'm gonna move the lower to 5. And then I'm gonna calculate the middle. The middle gonna be 6. I'm gonna check this if it is bad. So I'm gonna send 6 to the API. API gonna say true, right? Because if 5 is bad, 6 is gonna be bad, 7 is gonna be bad. So the API said it's true, but is this, because what I'm looking for is the first bad version. Is this the first? I can't say, I can't guarantee, right? Because there's still another version before we did not check yet. So because this is bad, what's gonna happen is we know that how to do it. We know, because this is bad, we know that the bad version can be here. The first bad version can be here, right? Why can be here? Because maybe this is not bad, right? So if I check 5 and it say false, automatically I return 6, because then okay, 6 is the must be the bad one. But if I check 5 and I find that is true, that means it's bad, then automatically I know that 5 is the first bad version. So if we're gonna do it with binary search, we're gonna do the same thing.
Sorry, can I ask something? What
Yes,
about
please,
if you check the middle and it's bad?
Which means 6? The middle here, 6?
4. Let's say 4.
4.
And it's bad. Yeah.
Yes.
It's bad actually.
Yes.
So what about if 3 was bad?
Yes. Okay, let's hold down on that idea and we treat that
I don't know.
I mean, let's hold down that idea. Let's finish this one and come back to the case where 4 is bad.
Okay.
So we said now we know that 5 is bad because we were doing this simulation, but the algorithm doesn't know. We are just looking. We need to send it to the API. So in this case, we check the middle, which is 6. It gave us like true. Then we know it is bad. Okay, do I end here? No, I'm not gonna end because I need to check 5. And 5 can be either true or false, which means either bad or not. If it wasn't bad, I'm gonna return 6. If it was bad, I'm gonna return 5. Because I'm sure 4 is not bad. Because we check it in the beginning, right? We are sure this side is not bad. So it is somewhere here. Now, if we are following the binary search, it's gonna be the same thing. 6, I'm gonna check the API. What it said? It said true. It's bad. Okay. Then we know this is bad. I need to remove the high. When the middle is bad, I'm gonna move the high. Now, do I move the high here or here? I'm gonna move it here, right? Because if I move it here, that means like if I'm treating this not bad, because I need to include it because it is bad, and because I don't know if 5 is bad or not. Because if I move it to here and then I check 5 and 5 end up not bad, if 5 end up not bad, I lose track of 6. I can't go back to 6. So I'm gonna move the high to middle. Right, now I'm gonna loop and calculate the middle again, which automatically gonna be on 5, right? And then I'm gonna check 5. Is 5 bad? It's gonna say true. Now that is true, I will just move high to here, or like, yeah, I think I move high to here because that's what we did before. So high is gonna be always move to the middle. Then the loop gonna stop because now the high, the condition high and low are in same position. That's when the loop stop. Then I'm gonna return 5. But let's roll back a step and let's say the 5 is not bad. So we are in this condition. right here, and this is not actually bad. The actually bad one is 6. So we check 6. It's a true. It's bad. I'm gonna move again high to here because I wanna check 5. I don't know if it is bad or not. Now I did check 6. I move this. I loop. When I loop, I calculate the middle again. Now I'm gonna send 5 to the checker. The API is gonna be false. Okay. Now 5 is false. Interesting. Now because 5 is false, I am sure it is 6 gonna be what is it called? 6 gonna be the bad one. So I'm gonna just move left to the mid +1 and return that, or just return high. I don't know. It depends how we're gonna code it. It's clear.
So if I'm getting you right, what you're doing technically is that if it's good, that's if it's bad is false, you move the low pointer or the is good pointer. That's how I'm picturing it in my head.
Yeah. Okay. Let me maybe write it. Let's write. So we said we're gonna check if is bad version. So this is how we check, right? Let's say X. If it is bad, so if it is bad, that means 6. If 6 is bad, what I'm gonna need to do? I need to move the high here. So high gonna be equal the middle. Else, when it is not bad, right? When it is not bad, for example, we were in this condition, whereas 5 is not bad, I'm gonna move the low to mid +1. So the low gonna be mid +1.
So that will work any case where that value is not bad.
That will work in any case that value is not bad.
So what I'm saying is that if the value is good, you always move the left pointer towards the towards the right.
Yeah, because if 4 is
right.
Yeah, because if 4 is good, I automatically do like this, cut this. So
Okay,
the
yeah,
low become here.
Okay.
But
so that you can trim it down. Okay.
Yeah, but if,
So if it's
4
bad,
was
you move the
bad,
high pointer.
I need to keep it, right? I do like this.
Yeah.
I remove this,
Yeah.
but I leave 4 because maybe all of these are good, and only this 4 is bad, or like 4 is the first one that's bad. So I always want to keep it.
Yes. Makes sense.
Now let's go back to the example that Pascal said, which is 4, I believe. Okay. Okay, so 4 is the middle, right? And I believe Pascal, you said 4 is bad, right? So secretly we know that 4 is bad. So if we know 4 is bad, automatically we understand, okay, all of these are bad. But maybe one of these are also bad. Maybe this is bad and this is bad and this is only current one are good. In that case, if this is only one is good, we need to return 2 because we are looking for the first bad version, which is 2. Or maybe 3 is the first one version and this is all good. Or this 3 all good and the first one is actually 4. So because there's chance this is all good, we will keep them. So we're gonna cut our array in this side. How are we gonna do that? We're gonna move the high from here to 4. Now we're gonna calculate the middle, which gonna end up here. Now let's see. 2, it's not gonna be bad, right? Because we know that the first bad one is 4. I mean, like, we know from this perspective, but algorithm doesn't know. So 2 is gonna return false, which mean automatically we understand this part right here is clean. So I can eliminate this, which mean our array gonna become like this. How I can do that? Just by moving the low to here. Now I'm gonna loop, I'm gonna calculate the middle. It's gonna end up on 3. I'm gonna check the API, gonna say 3 is clean. Okay, nice. Our array gonna close up right here, which means the low gonna end up right here. It's gonna return 4. Hope it's clear, Pascal. I think Pascal sleep. Okay, let's go. So we know this is the basic, but we need a while loop, right? Because this is binary search, so the loop gonna keep looping as long the low is less than the high. It doesn't cross it, right? If it cross it, if they cross each other, the loop should stop. And that also mean when they are both in same position, right? So it's gonna be low less than high. So when they are in both position, in same position, it's gonna stop the loop. That is our target. So while let's call it left, low, high, then do this stuff. If someone finding a really hard time to catch up with us, there is this PLD binary and someone else that we did go through this binary search. I think this one binary. Let me post the link. Okay, so let's come back. Is this all? I guess this all, right? So we just need to define low, low, high, low. Let's do a tuple low, high. It's gonna become low, low. We're gonna start from low, from index 0, right? And the high is gonna be the length. Wait, I'm confusing myself.
Just use index
the length,
minus
right?
1.
Length minus 1.
The length of what? Wait. Oh, there is no length.
Oh, we have to generate our own list.
Okay, so I don't think this is how it's gonna be. So, oh, it's gonna be n. It's gonna be n.
N minus 1.
N minus, because it doesn't start from 0. It starts from 1. So if they say n5, that means we have array 1, 2, 3, 4, 5. So it's 5 elements, right? If I did minus 1, it's gonna be 4.
We only have index 4. So high will be the last index, which will be index 4.
Wait, what are you talking about? Index?
The index of the array.
At the end of the day, we will be accessing index 0, index 1, index 2, index 3, and index 4.
Where is the index? We didn't use index at all. We're given
at 0, then you need to start to give high n minus 1. But since you are talking high to be n, then low to be 1. Not
Wait,
zero.
this array is just for us to understand. There is no array. So
Yes,
basic.
exactly. That's why I'm saying if you start with zero, then you need to go up to n minus one to be with the same thing. But if you start with one, then height should be n.
Yeah. So and the height should be n, right? Because I'm
Yes.
gonna keep looping 5 times.
And then low should be 1 instead of 0, isn't it?
This one, the low.
Yeah.
Yeah, you're right. 1. Okay, that's what maybe what you mean. Maybe because if we did 0, then we'll do -1.
Yeah, that's right.
Okay, I misunderstand. But where is the middle? We actually didn't calculate the middle. Because every time we loop, we should calculate the middle, right? Now, can someone tell me how do we calculate the middle? How do we calculate the middle?
That's high plus low.
High
divided by
plus low divided by 2. Okay, so this will work, right? But the better way, or like a best practice, is to do low plus high minus low. Yeah, it's better to do this one than this one. Okay, let's read quickly about it. So the expression left plus right minus left split on 2 is used instead of right plus left split on 2 to avoid potential integer overflow. In some language like C, C++, and Java, the sum of right and left could exceed the maximum limit of integer if both right and left are large. This would result in an integer overflow, leading to an incorrect result. So like just to avoid this in other language, it's better to use this, but in Python we don't have to. Python, however, has arbitrary precision integer, so you won't run into integer overflow issue, but it's still good practice to use left then what's it called, left plus right minus left, just to avoid. I posted the document if you want to read it. Let's go for it. Let's go detail about it. You wanna understand more. But stuff like this can make difference in like tech interview, right? If someone writes the code like this and someone writes it like this, it can tell a lot about the person. You may even get a question about it, so it's good to know. Now we know how to do the middle, right? But what else is?
I think we need to increment the low or the high. I don't know. I mean, is it X for incrementing?
I think that will happen automatically when you are doing this low and high, right? Because every loop we move this.
Yeah, I think it's talking about the X, where X here is supposed to be the mid.
Oh yes, you're right. Yeah, the mid. But are we not gonna return anything? We need to return something. Wait, can you repeat?
Yes, after the while you should return either low or high, but normally it should be low, because at the end of the while loop, low should be equal to high.
Okay. Let's take this to the lab. Let's clean it. Okay, so high, low, high, low, high. But guess that's all. Let's run. Okay, nice. Submit. Nice work.
Nice, guys. Nice one.
That was really nice. But I'm curious how these people do it better than, let's say, somewhere like here. Okay, isn't this same code? What did it different? Maybe not tuple. Let's see if we remove tuple. So high is n. Okay, give me the code 1 second. 10. Okay. So let's do low equal 1, high equal n. Which is that's gonna make difference. Probably this formula.
I think that doesn't really. That's doesn't really affect.
Oh, that's actually made difference from 35 to 80. Okay. What about if we did the high plus low directly? That's gonna do any difference? Let's see. Looping.
Means unpacking actually consumes a lot of memory, I guess.
Oh, I forgot the loop.
The brackets.
I forget. Yeah, submit. Okay, maybe it's just random. Okay, guys, this was a nice LeetCode. Now the last LeetCode, the third one, is Ransom Note. And this one, I'm gonna drop it in the chat, and we're gonna explain it, brainstorm, and each one of us gonna try to code it, and we're gonna see solution of each other. Okay, so let's read it and see how we're gonna do it. By the way, we did it, I think, in the first PLD or something. Okay, Bank, thank you for joining us. Okay, so given two string, ransom note and magazine, return true if ransom note can be constructed by using letters from magazine, and false otherwise. Each letter in magazine can only be used once in ransom note. Okay, we have ransom note A, magazine B, false, because I can't create A with character B. Ransom note A, magazine AB, also false, because I need two character A and I only have one character. B, I can, true, because I have two A. So like imagine you have a magazine and you cut it to pieces, and each piece give you one character, A, B, and you wanna construct A, which is the ransom note, and this is the magazine. Now I wanna create A, so I have one A here, so I can create it. I need another A. Okay, I still have one here. I can create it, so it is true. But if it was, for example, just EB, I will create A. But when I come to create A, the second A, I can't, because I have only B. So it will return false. Okay, who doesn't understand the problem well? Or any question, anything? Okay, I guess everyone understands it. Okay, start coding, guys. Let's do it. Let's do it and see your
So was it,
solution.
if we have magazine like A B A.
Magazine A. So it's 2A or 1?
2A. The middle is B.
2A.
No, A B E.
A B A.
Yeah.
EBA.
Yeah.
And the ransom note?
It's AA.
AA.
It's true or false?
True, because I can cut this character, move it. I can cut this character and move it.
So we check.
Yeah, as long you have that character in the magazine, it should true.
Okay. Cool.
Okay, how are we gonna do this? Don't cheat, guys. Don't look at my code. Focus on your code. Oh, Ningas is hacker. Yeah, that done in a while ago. Okay, let's wait maybe like 5 minutes, 10 minutes. Okay, let's wait like 5 minutes, 7 minutes, and then we see solution. If you finish, post your solution in the chat. Okay, let's try the one that Ninga said, collection.
Equals.
Equals?
I forget. Is it equals?
Maybe. Let's see. Wait. But the magazine can have. It can have.
Yes. You're checking the union.
So if I did minus.
Dot subtract, it's got its own methods.
It's what? It's not a method. I did see something like this. I forgot.
Yeah, you can go to the documentations. The documentations for counter will give you the kind of you can't use the minus, but you can use the dot subtract if you want to do that.
Okay. Return collection count. Oh, what? True. False. PB. Okay. Oh, okay. So left less than equal. Subtract. So you subtract and you see. Okay, let's not go there. I feel like it's deeper than my brain. Okay, who is finished? Let's see solution. That's it, just the coach and TD and Sabah that did it. And the Ngasi with the hack. Okay, let's see the first solution. So hash. So we have hash. Okay, let's take it here so we can understand. We check if the length is 0. Why is this? Why does the length 0 check? Because the magazine is empty. Oh, so we return false. Okay, that's smart. Hash map, hash magazine, hash ransom net, and then for E in M. So you're gonna loop on the magazine. So for example, the magazine is A, B, and the ransom net is A. You're gonna add. Okay, so you're gonna add this element to the hash magazine, which gonna be what? It's gonna be, in our case, this is R, this is M. It's gonna be A1, and then second character, which gonna make it A2 and B1. And then for E in ransom, you're gonna add again the same hash map R, and it's gonna have A2. And then you're gonna loop through the hash ransom net, and you're gonna compare each value with this. If the A2 is great, then false. Okay, so if it doesn't exist, it's gonna compare it with 0. Okay, that's smart. That's nice work. Okay, what other solution? Okay, this is straightforward. So this one is hash map. Okay, so if it's not, it's gonna add it, and then you're gonna compare if char in the hash map, and the hash map is less than 0. We're gonna do -1. If the hash map is return false, if the character it doesn't okay, yeah, so if the ransom note doesn't exist magazine, it's gonna return immediately false. Okay, that's good. Okay, who's confused about this code, or like didn't understand something in this code, or like didn't understand the solution? We can explain it. Anyone have any question? Okay, what's this one? Okay, this is kind of the same. Next PLD. Okay, the tech PLD or the C13 PLD? So C13 gonna be Tuesday and Friday, and next tech PLD is tomorrow. Okay, let's see this solution. What is this? So you count the character. Okay, that's smart. So you just count the character and then you say if you have enough. If not, return false. Okay, if anyone have question or anything, we can keep going. If not, we can end the PLD here. Tomorrow, same time. The next PLD tomorrow gonna be about climbing stairs, longest palindrome, reverse linked list. It's gonna be fun.
Are we stepping up the difficulty? Are we off the easies?
You're still easy now. Like this week, it's gonna be easy. And then week 7, where we're gonna lose some hair.
Alright.
Yeah. But it's gonna be fun. I think every week we're gonna have more muscle memory. So like we're definitely we're gonna fight with this. Child play. Okay. So tomorrow we're gonna see what? Where's climb the stair? Yeah, that's it. Thank you for joining. Hope you guys enjoyed this PLD. And if you are in core 13, don't miss Tuesday, Friday, right? So Ningasi, Tuesday and Friday.
Thursday.
We continue the Odin project, and tomorrow we do tech PLD.
Thursday.
Thank you.
Thursday.
Have a good night. Love you all, guys. Bye.